Okay, let me share my screen. Everybody see it? Okay, is that square clear? The screen, everybody see it? Give me some response. Okay, I see it. Response from Jamal. Okay, good. This is the equation we introduce. Okay, notice, really important to attending today's class. I'm combining chapter 7 and chapter 10 together. Okay, give you an overview of the piping system, and so really need to follow me. Okay. So this is the drawing is a typical piping system with a pump. Okay, supply the energy to the pump. To the piping system, okay, to deliver liquid from lower location to higher location, okay, also to produce some speed, okay. So this is the governing equation guiding the whole process. This process also including a turbine process. If you take energy from the water liquid system, okay, you use the turbine. So this is the typical example, water flow from high location to low location. So from the potential energy, create the kinetic energy, then the kinetic energy drives the turbine and to produce electricity. Okay, so this equation, general energy equation, okay, in the piping system, governing the both process, pump and the turbine. So in the equation, in addition to the Bernoulli equation form, you actually it's a Bernoulli equation plus 3 terms. Okay, so the energy supplied to the system by the pump, we use pump head to represent it. If you have a pump before, you see the manufacturer give you a pump curve. Okay, pump curve basically is the pump head versus flow rate. Okay, how the pump will perform. So HP is the pump head. Okay, so how much energy is supplied to the system. Remember, when you do calculating the piping system equations, piping system problems, always use this form, head form of the Bernoulli equation. Okay, it will be convenient to you because that's the convention. When people talk about it, they always talk about the head, pump head, turbine head, head loss. Okay, sure, you can do the pressure equation. Then your pump head here is the pressure, is the pump pressure. Okay, instead of the head. Okay, but most of the time people in industry like to use the head to talk about the piping system. Okay, so this is the head form. So every turn has the unit of length. Okay, meter or feet, right? So pump head is in the left-hand side. Right-hand side is the turbine head. If you have a system with a turbine without pump, you don't have the pump head then. Okay, head loss. For every system, you will have the head loss. Okay, whatever, you will have a frictional loss. Okay, so loss can be modeled. Okay, so this is the entire whole picture of the loss. That one term in the energy equation, HL. Okay, we can calculate HL, use this model. Okay, HL the loss has 2 parts. One is the frictional head loss, so the HF, okay, plus the minor losses from the fittings or all kind of components attached to the piping. So everything you put it on the pipe will contribute a little bit of the loss, okay? So for head loss, for the frictional head loss, you have an equation here, okay? For the minor losses, you also have the equation. Both of them will be v squared over 2g. Okay, velocity is there. So velocity will have effect on any of the losses. Okay, and both has a coefficient, frictional coefficient and the minor loss coefficient k. Okay, k is from the table. I think, let me give you the table number on the textbook. I can text you. Okay, hold on. I have a paid table in my computer. Okay, I'm texting you the in case you don't have the figure and the tables now, I'm texting you now. You can take a look in our group chat. Okay, this is one of the table I'm sending it to you. Please take a look. Okay, table 10.5 in the textbook. It gives you the case, okay, the case for each different situations. For example, pipe entrance. The entrance, even the entrance will give a little bit loss, okay? Contraction, if you have a contraction, then there will be some loss due to that contraction part. Expansion, same, okay? Bend, okay? You'll have some loss in the bend. And the 90-degree middle bend and the 90-degree smooth bend, they have different case, okay? For the smooth bend, you see the K is related to the radius of the bend of the turn, okay? So, and also there are other fittings and other pipe fittings, including the valves, all kinds of different valves, when it's wide open and the half open, the T, the elbows, everything will contribute a little loss to the piping system, okay? But to me, it's easy. Basically, you just look at the table, okay, find the K, and put the K into this equation to find the minor losses, okay? And the K times V squared over 2G. That's why I put a summation here, summation K. So you have many different Ks, okay, all put all together, okay? Very tedious work. Some of you have some industry experience, you already know. If you do the piping calculation, you need to count how many elbows, how many bands, how many valves, okay, those kind of things, right? Okay. I'm sending you another one for the frictional coefficient. Okay, did you see it? This is the famous Moody diagram. Okay, it's in the textbook. Okay, if you have a textbook, any type of textbook, you should have this diagram. Okay, so take a look. Let's go through, look at it, see how you use it. Okay. Everybody, do you have the diagram on your cell phone now? Are you looking at it? Please follow me, okay? So in my class, yes. Any questions? Good, okay. Are you looking at the diagram? Okay, so how to use this diagram? You need to use this diagram in your final exam, okay? So F is the y-axis in the left, okay? That value is F, look at that, right? The value of F from about 0.08 to 0.1, okay? So that's on the diagram, the range. So everything has a little loss in there. 0.008, I think is the minimum here, okay? The x-axis, okay? Are you looking at it? X-axis is something called Reynolds number. We mentioned it in the beginning of the class, Reynolds number, okay? So you need the Reynolds number. Okay, Reynolds number is velocity times the diameter in the pipe divided by the kinematic viscosity. Or if you use dynamic viscosity, be careful. Rho VD divided by dynamic viscosity. There are two viscosity on the tables usually, okay? One is called dynamic viscosity, it's a mu. The other, the kinematic viscosity is called nu, okay? So if you use kinematic viscosity in the numerator is velocity times diameter of the pipe. Okay, so for every pipe, if you're given velocity, if you know the flow rates, you know the diameter, and you know what fluid is in there, you should be able to calculate a Reynolds number. Okay. So the Reynolds number is the x-axis of the Moody diagram. Okay, so it also related to the roughness of the pipe, right? We're talking about friction. So what kind of material of the pipe dictates the roughness, surface roughness, okay? So the vertical, the y-axis in the right side of the diagram is called relative roughness. It's K over D, okay? So this is right vertical axis. Let me send you another table. So now this is very practical. Those different material has a roughness. Let me show you a table in the textbook. Okay, everybody, do you see it? It gives you, if your pipe is made of these materials, okay, each material will give you a surface roughness. Okay, okay. Be careful the units here. Okay, in SI unit it says the millimeter. The roughness is really small, right? The surface roughness is really small, so it's in millimeter. Okay, then the other column, if you use English unit, it's in inch. Okay, so but let's come back to the Moody diagram. Moody diagram is not directly using the K in the table. It's not the roughness, it's the relative roughness. So it's the roughness divided by your diameter. Let's use the capital D, since I use the capital D above. Okay, so that value you need it. So look at the Moody diagram now. Those blue, you see in the diagram, there's a lot of blue lines, blue curves, right? Each blue curves represent a different roughness, relative roughness, K and over D. Okay, so what you do, what you try to use Moody diagram, what you do is find your surface roughness first. Okay, then pick a curve, blue curve, represent your surface roughness. What about in between? Okay, if your roughness is in between two curves, that's fine. You can interpolate a curve. Okay. So find the blue curve first using your surface roughness, okay? Then calculate your Reynolds number, okay? So based on the Reynolds number, okay, on that blue curve, okay, then you can find the F value, okay, for that point on the blue curve, okay? So pick the blue curve first based on the relative roughness, then find your Reynolds number, okay? Get a point on the blue curve, okay? Then go to the left, you will see your surface roughness, F. I'm sorry, friction coefficient F. Okay? Any questions? Okay, everybody need to know how to read the Moody diagram if you graduate from my class. Okay, any questions? Is that clear to everybody? Give me some response. Good. Okay, good. I see response from Devin. Good. Okay, so very practical. You can actually, with the knowledge for today's class, you can go actually work in the industry. Most of the job for mechanical, basically fixed equipment and what rotating equipment, right? They all related to the pipe. Okay, I think mechanical usually work as a reliability engineer in the local industry. So chemicals, of course, you definitely need this. Yeah, you're doing the piping calculation all the time. Okay. Okay, this is Moody diagram. So now we know how to calculate. So in a practical piping system, basically your task is actually to identify the overall loss. Okay, very important. You need to know how to identify the overall loss. Okay, for a piping system. The loss has many components in your piping system. If you have a practical system, very complicated, you have 20, 30 components for the case, okay? Maybe you have a different size of the pipe in the whole system. You have different F too, okay? So it will be a very tedious work. You really need to be good on Excel, okay? At least put in every calculation in Excel. Okay, one more thing. This is the loss. I think that's everything about loss, okay? One more thing is here is a pump head and a turbine head. How do you convert head into power? Okay, basically, the question here, most of the time when you need to do this kind of calculation, one of the purposes is for you to select a pump. Okay, based on this equation, you can calculate the pump head required by the system. Okay, is that right? Pump head required by the system. Then after this, the goal is actually to find out what the power required for the pump to make the system work. Okay, so there's a conversion from the pump head into power required. So if you know the power required by the pump, then you can actually find a pump. Okay, pump, how much horsepower, this pump is to make this happen. So the conversion is this: power equals to, of course, something pump head, right? Okay. Flow rate matters, okay, and the gamma. What is gamma? It's the property of the fluid, right? Rho g, specific weight. Okay, so you need to memorize this equation. Okay, you need to memorize. Final exam is a closed book exam, so the basic equations you need to memorize it. Okay, so I will provide you the diagram, like a Moody diagram, all those tables. Sure, I will provide everything, like this, but you need to memorize probably the 10 equations we covered in the semester. Okay, not much. So this is one of them you need to memorize. How to convert. So from the piping system equation, you calculate the pump head required to drive the system. Then you need to do this conversion into the power, actual power in watt or in horsepower required to drive the system. Okay, so very practical here, very practical. I just want you to fully understand this class. The entire 75 minutes of the class, I want you to focus, pay attention, and remember. Okay, this is the equation to convert HP into power. Now, you know the horsepower needed for the system. Then you can do a pump selection. Pump selection 101, basically. You need to know how big a pump you need. Okay? Everybody follow me? Okay, very practical, very useful for you. Okay, this is good information. Okay, these are all the equations in the topic, piping system. I think it's about it. Okay, how about the turbine? Turbine, the same equation. Turbine power. How much electricity, how much power it can generate. Same thing, turbine head. For turbine, same thing, gamma times HT times flow rate. Okay, again, see flow rate is in there. Flow rate matters, how fast it goes, right? It matters, the fluid. Okay, so that's electricity power it can generate. Okay, from a turbine. Okay, turbine and a pump. They are basically the same idea, but it's one in the right-hand side, one in the left-hand side. Pump is supply energy to the system. That's why it's in the left-hand side of the equation. Turbine is taking energy from the system. That's why it's in the right-hand side of the equation. Okay? Any questions so far before we move on to some examples? Everybody good? Okay, with this set of the equation? Okay. So we have three equations here, basically. The governing equation, the head loss model, and the power equation. Okay. There's some detail in the head loss. You need the minor losses case. You need the frictional head loss F from Moody diagram. Okay. Okay, let me start a new page with all examples. If I can finish today, I give you more examples on Tuesday. Okay, but these are really good examples for you. First one, let me give you an example from chapter 7. Okay, 7.3. Okay. It says this. It's a typical piping pump system, piping system. Okay. It give you the I think what it give you the flow rate. Okay. Flow rate is 0.5 cubic meter per second. Okay. What else? It's water. Okay. This is the pump. Okay. At the inlet, the elevation, this is 1, this is 2. Okay. Again, you apply Bernoulli type of equation, you always have to have 2 locations to compare, right? Z1 equals, it says 30 meter. Yeah, 30 meter. P1 is 70 kPa. Okay. At the 2, Z2 is 40 meter. So it's a little bit higher. P2 is 350. Well, this is the really, really practical problem. Look at this. You have pressures. Usually you have pressure gauges everywhere on the piping system, right? So you can read the pressure easily, okay, in practical situation. So what power in kilowatts needed to supply by the system by the pump? Okay, how big does the pump need to be? Okay, what's the power needed? So it's reasonable, right? Without the power, it won't work, right? Yeah, it's not possible to drive the water from lower location to higher location or increase the pressure even from 70 kPa to 350 kPa. Without the pump, it's not going to happen. So you need a pump. Okay, pump supply the energy to it. If the pump is too small, it's not going to happen. Becomes 350 output power pressure, right? It's not going to make the flow if the pump is too small. Okay, so there must be a pump selection here. You need to select the pump. If you are the engineer, your boss want to make the system work, it will ask you, hey, how big a pump I need for this? Okay, how much in kilowatt, how much in horsepower I needed for the pump. Do you know how to do it? If I give you as a quiz problem now, do you know how to do this thing? Do you know how to write down the equation at least between 1 and 2? Everybody knows? If everybody knows this, I can make it as a quiz. Go through this problem. Let's make it a 5-point quiz. Is everybody good with this one? Let's go through it, but also as a quiz. See if you can do it. Okay, I want you to write down the equation between 1 and 2. Okay. Equation between 1 and 2. Let's make a 2-point quiz. I go through it with you. Don't want to give you too much pressure here. Okay. Let's write it down, and I want you to go through it. Okay, do I have all the information? I think I didn't give you the loss. Okay, hair loss here is given. You don't need to model it. It's 3 meters. Okay, one more information here. So write down the find the equation. Write down the correct equation between 1 and 2. Okay. Then substitute, putting all the values you have. Okay, I think you need to calculate the velocity. So I need to give you diameter, right? What it says, a pipe. Okay, diameter. Diameter is 50 centimeter. Okay, so write down the equation here. So it's a Bernoulli equation. Okay, does it has turbine head?
No.
Okay, good. So you don't need to have the turbine head in there. Does it has pump head?
Yes.
Yes. Okay. Does it have hair loss?
Yes, it was given.
That's good. Okay, so I assume everybody can write down the equation, right? Okay, write it down now. Okay. Yeah, please work with me. I'll give you 2 points for the quiz. I think everybody will get the 2 points here. Okay. Now, you need to calculate the velocity. Okay, go ahead, calculate the velocity in this thing for me. Okay. I think the only thing in the equation you probably don't know is the velocity, right? Water, gamma is 9,800, I think easy. In the calculation, be careful. Pressure, use 70, don't use 70 kPa, use 70,000, 70,000 Pascal in the calculation, okay? But now, calculate the velocity for me first. You need to calculate the velocity. You have the flow rate, right? You have the diameter. Can you calculate the velocity value? I want you to follow my steps here. Okay, I don't want you to, some of you have textbook, just copy textbook. No, I won't give any points if you copy textbook. Follow my procedure. I just want to make sure you follow me in the class, okay? Then I award you with points. Okay, now, next is to substitute the values into this equation you write down, okay? This is the velocity, this is the equation, this is the velocity. Now, substitute the values to calculate the HP. Okay, this is the third step. Substitution of the values, known values, velocity, pressures, okay, elevations. So HP is your only unknown in that equation, right? Go ahead and calculate HP now.
So that diameter is constant?
Yeah, I'm a constant.
Okay.
50 centimeter all the way through. Notice I skipped some stuff from chapter 7. We're assuming the practical conditions, so there's no alpha in the equation. Okay, alpha is always 1. In the equation, if you just read the textbook, it will confuse you. It will have a lot of information about alpha and anything. We simplify it. We just use the regular case without considering the alpha. Okay, so follow what I said in class. Okay, you don't need to worry about the alpha. That's why I want you to come to my class. If you're just reading book, learn by yourself, you will spend a lot more time. Okay, did you calculate the HP?
I got a question.
Yeah.
If you can't answer it, that's fine. I'm just trying to figure out, since the diameters are the same, the 1 and 2 velocity is the same velocity?
Yeah, of course. Conservation of mass, right? Yeah, that's the same.
I was just trying to figure out why you had us find it.
Well, you give you one flow rate. The flow rate has to be the same based on the principle conservation of mass. No matter how big a pump is there, if the discharge velocity increased, the suction velocity also increased. So it will always the same for the flow.
So then that's 2 things you want us to calculate what the velocity is, because it just cancels out in the if it's the same,
That's what
cancel out in the formula.
Yeah, probably you don't need it, but I want you to calculate. That's why I want to make it something different compared to textbook.
That was something I was thinking about, that the only unknown, but one, I mean, okay, I got you.
Yeah, that one makes something different. Okay, but it's a quiz. Otherwise, you just copy the textbook. Okay, So HP, okay, hope you do some calculation, calculate it. Then the next step is to find the power required. Okay. Go ahead, do some calculation, write it on the paper and take a picture. Let me open the summation site now and you can submit. How about that? This is the easy 2 points for everybody, huh? Make up a little bit of your score. Let me get the quiz 12, right? Okay, let me make the summation site available. Now you can submit. Today is what? April 29th, right? Okay.
This should probably be a 5-point quiz, I would say.
No, it's 2 points. That's kind of too easy. Okay. Okay. Anyway, but the meaning of this is, you know, it's you calculate actually a practical piping system like this based on the information, based on the Bernoulli's, based on the actually we should call the energy equation in the pipe. You should be able to calculate the power needed to supply to the system to make this work. Okay, basically that's the principle of pump selection. Okay, how much additional power you needed, okay, to make it happen. So then you can find a pump to satisfy that. Okay, is that good for this one? Everybody, any questions? Okay. So I want you to fully understand not only solving this problem, but also the concept-wise, okay, what this principle used for, okay. The turbine problem is the same. I don't want to give you another one. Basically, just calculate in the right-hand side for the turbine head, right? Okay. Okay, let's do a problem using Moody diagram. I think you need it, okay. You need to know how to do that. Let me give you example. Can I continue? Everybody, are you done?
No, sir, not yet. I'm almost done though.
Okay, I'll give you 1 more minute. How about that?
Get like 1:30.
Okay, how about 2?
Let's make it 3, and you gotta have.
No. Don't. Too much. I have still a lot of stuff to cover. So, yeah. Okay, I see some summations already. Okay, yeah. 1 more minute.
A question. I may be out the Zoom just because I'm using this phone to upload it.
Okay, that's fine. By the way, I already assigned the set of homework problem, last set of homework problem from chapter 7 and the 10. Okay, it's about probably around 10 problems. Okay, I will strongly recommend you to prepare it. Okay, I feel to practice it. I feel this is an important topic. It's not saying that for the test or what, it's good for you to know. Okay, these are the, I think, some applied knowledge.
Since we just learned it, you should probably put a question on the final just like this one.
Well, this probably is too easy for a final exam. You know, final exam probably will be a little more difficult than this, but it should be comparable to some of the homework problem level. Okay, so that's why I say it's important to practice some homework. Okay, yeah, I see most of you submitted.
How many questions are going to be on the final?
That will be 5 questions. You have 2 hours. So it's like what, 24 minutes for each questions. Okay, so time, you need to manage the time well. Okay. Devin, what's your question here?
What could you do to this problem to make it more difficult, just as an idea?
Okay, I think it will, one of the thing I can tell you the entire class is to adding the head loss model there. So if there's a components, you need to find out those friction coefficients, K's, okay, then put together to calculate the head loss. This one, head loss is given, right? So basically just one equation problem. Then it could be also the diameter of the pipe, the size and the suction and the discharge is different size of a pipe. Then you have different friction coefficient. They have different velocities, okay? These are all the added difficulty it could be for this problem. Okay, yeah. Did I answer your question? But all of them are not that difficult, right? Think about it. Even I change the pipe size in the discharge, the velocity you can basically calculate 2 times. The flow rate is always the same, so you can
Right.
calculate V1 and the V2. Okay, then based on the
So it's not
V1,
really more,
yeah.
so it's not really more difficult. It's just more time consuming.
Yeah, then more time consuming, more detailed, but it's not
Right.
difficult. Come on, I always want, you're good now. You're kind of said it's not difficult. I just want you to have everybody have that feeling at the end. All those problems I give actually is not difficult. Okay, if you remember all those equations, all the details, it's not difficult, really not difficult. Okay, so that's the feel I want you to guys have. Okay, good, Devin. I like that. I like what you said.
If you, like you said about having 2 different diameters and velocity and stuff, and it gives us a different K coefficient, which K do we use in the head loss? The K at 2?
No. Hold on. That's a good question here. Let's look at it. It should be this. Strictly speaking, this is friction loss. I should put a summation here. Okay, so it actually is, I should put a parenthesis here. Okay, it's a summation of the whole thing. So every component has a loss. Okay, every component has a K. You have to use the velocity that goes through that component to calculate the loss. that make sense? So for example, you have a diameter here is larger, diameter here is smaller in the discharge, okay? D1, D2, okay? Let's say the D2 in the discharge of the pump, this diameter is getting smaller. So basically you have two portions of the pipe. So for the frictional loss, you have to also calculate separately. For the larger diameter portion, you have a different friction coefficient and you have a different velocity. Okay, then for the small diameter portion of the pipe, you also have different friction coefficient, different velocities and the different diameters. So each portion, if you change the diameter, each portion you have to separately consider. Same thing as the minor losses. If you have a valve here, let's say possible you have a valve here. So with the K of this valve, you need to use the velocity goes through that valve, okay, to calculate the loss of this valve. If another valve, gate valve is on top of, on the suction of the pipe, then you use the suction velocity and the suction K, okay, for that valve. Valve, the K is the same, you know, but with different location, you will have a different velocity going through that component. Then the loss from that component will be calculated separately. Okay, think about which velocity goes through your component. Then it costs the loss, you know, due to that velocity and the K. Okay, that makes sense, Patrick? Okay, so it's very practical. Okay, I want you to, you know, really today's lessons, the practice I gave you, chapter 7 and chapter 10, basically you can actually work in industry as an engineer. Okay, really, I'm serious. This information, if you feel really good, okay, even you don't know much of the calculus, you still can work a lot of jobs there. Okay, very important, practical. Okay, let's move on to 10.3. Okay, I want to show you an example how to use the Moody diagram. Okay, Moody diagram is really famous. Everybody knows Moody diagram. Okay, as an engineer, mechanical engineering industry. Okay, so let's say 10.3 is really easy. I think I would just want you to practice it. The length of the pipe is 1,000 meter. Okay, diameter is 0.2 meter. It's kind of like a big pipe. Okay, the material is asphalt cast iron. How to spell? Asphalted cast iron. Okay, pipe. Okay, so water flow rate. This is the water flow rate is 0.05 cubic meter per second. Okay. What else? That's it, right? 27. That's what is the head loss? Okay, so what is the head loss? Okay, so this head loss basically is only considered the frictional head loss. Okay, basically I can change it to here. Then nothing, no components on there. So this is basically frictional head loss of this pipe. Okay, I think you should be able to know how to do it, right? So write down the equation. You have to memorize that equation. In the test, you need to memorize the equation, right? Loss equation. Anybody? Can you memorize it? Can you say it now without looking at your book? Sometimes I can help you remember stuff. See, this equation, every terms in the equation is a help, you know, it's contribute to the loss, right? You know, this equation definitely have the friction coefficient, okay, right? Friction coefficient, okay. So what other things affect the frictional loss? Does the length affect it? Does the longer the pipe is, more loss it is?
Professor, what is that Q equal?
0.05 cubic meter per second. Okay. Think about, I'm helping you remember stuff. Okay, think about what affects the pipe loss. Does the length of pipe affect it? Is the pipe longer it goes, it have more loss? Yeah, of course. So it's proportional, right? So the longer it goes, it have more loss. So it's proportional. If it's proportional, it has to be in the numerator, right? The length is proportional to the loss. So the longer it goes, the bigger the loss is, the length has to be in the numerator. Is that right? Okay. So what others affect it? Does the diameter affect the loss? When you buy a pipe in your house, you want a bigger pipe or you want a smaller pipe? You want a larger size? You want those 2-inch ones, or you want just 1-inch pipe, or 3/4 of the inch? It's cheaper, 3/4 of the inch pipe, right? You want a bigger pipe, okay? Always bigger and more expensive, but you want bigger because it has less loss. So diameter, the size, is inversely proportional to the loss. Is that right? Is that inversely proportional? Okay. So it's inversely proportional. Where does it be? Where should it be? In the numerator or denominator?
Denominator.
Yeah, denominator. That's in here. Okay. What other? And one more factors will affect the loss. It's your velocity, right? Is the faster velocity it goes, you have more loss, or slower velocity it goes, you have more loss? Okay, see, we're learning this concept right here, just using the equation. Okay, the faster it goes, you will have more loss. Okay, remember that if you don't know. Usually you turn the water really, really slow, then basically there's not much loss. Okay, so the velocity is also in the numerator of the equation. And the velocity is square. Okay. Okay, that makes sense? Okay, so
I have a quote. I got a new computer, just cuts out randomly. It cut out when you were talking about that you should have put the summation of K, and I missed. Are you talking?
Okay.
So I was going to ask that question anyway. Do we have to refer to the charge for each K value, or do we sum them up, divide by D?
No, not sum of the divided by D. No, you mean K, right? K or F? What are you talking about? K just times V squared over 2G. Think about K times velocity. The whole thing is the loss. So K is a property of that instrument, of that component. You need to know the velocity passing through that instrument or the component to calculate the loss for that part.
We sum up like in that it would be, we'd have to use the roughness of the pipe, the 290s. If there's a strainer in it or anything like that, that'll all go into that'll be counted in the K, right? Or
No,
that's just roughness of the pipe.
No, that will be counted into the frictional head loss. Remember, you have two components in the head loss. It's frictional loss and the minor loss. You're talking about the surface roughness, everything is frictional head loss. It will be included in the F, friction coefficient.
Okay, well, is all of that, do you sum up all of the friction losses?
Yes, if you have different portion of the pipe with different diameter, you have to calculate each section separately and sum them up.
I'm mainly talking about to read those charts, like the last step. The first step is you said find the surface roughness, and then go down, find the F value. Would that be a summed F value, or you find the F value?
No, each portion, no sum F value. Each portion, each one will have. That's why the summation is outside the parentheses here in this equation.
Oh, okay. I just wanted to make sure.
Yeah. Very important. Very good question. Practical. When you actually do with practical problem in the industry, if you get a job there, they have like hundreds of different portion of pipes in a system, very long, very complicated. What if your boss asks you to actually calculate the loss for the whole piping system? So you're gonna go to the site to measure, or they got you information already. Each portion, different portions. Okay, if they change the size, then you have to treat them as separate portions. Okay, so each portion, you look at the length, diameter, velocities in there, and find the F, and then calculate the loss for that portion. Then move on to the next portion. Okay, something like that. Okay, so you basically, I think you need to know the velocity associated with the portion of the pipe you're looking at. Okay, also the velocities that associate with the components. You're looking at each k. Each component, there's a velocity passing it. Okay, so the k times the velocity passing that components is the loss of the components. That makes sense? Everybody? Give me some feedbacks. They're good? Is that clear enough, everybody? Okay. Seems like it's a good for everybody. Good.
Professor.
Yeah.
I had a question.
Yeah.
On any of the quizzes this semester, has anyone got a perfect grade? Or like on the projects or anything? Is that even possible?
No. I don't want to disclose any information of the students' performance in the class. Okay, I cannot. Okay. I can answer your question about you, but no. That's not fair. Come on. That's privacy, right?
What was the question?
You want to know everybody, other people's performance. Is that possible to be perfect or anything like that? Okay, but try your best to do your job. Okay, I guess.
I do have a question about those projects.
Okay.
Has anybody ever did a project on cavitation?
Nope, I don't remember that. I can answer you. I think that for the project topic, probably. I think cavitation is actually a good topic to go, but it's not that easy to do.
It might be hard to do,
It's
like an
hard to do.
at-home $5 experiment.
Yeah, it's $5 experiment wise. It's probably not feasible. You have to control the pressure to be very low. Okay, so you need to actually have the equipment to make cavitation happens. So if you think about it, the pressure is really low, then some safety issues. I don't know. So usually, unless you have equipment in, it's difficult to do. Okay. Let's move on to this problem. Okay, now let's continue. I want you to do a practice here. You probably need to do 24 minutes in the final exam for a problem more difficult than this. Okay, so I want you to right now practice it. Let's see, for this problem, can you find the F for me? Do you know everything else? Let's look at it. Do we know length of this problem? 1,000 meters here. Okay, we know it, right? Diameter is given. What is the velocity? I want you to calculate the velocity first. Let's see. Can you try it? Don't look at the book. Try it to see how many minutes you needed to do the calculation. Think about 24 minutes for each problem in your final exam. Okay, go ahead, do a calculation for me. See if you can get the correct answer. Velocity. You're given a flow rate, given diameter. You got it? What is the value? Anybody? Yeah, try it. Okay. I think the velocity will be equal to flow rate divided by area, right? Okay, you need to be very quick to find this area quarter pi d square. D is given 0.2 meter, so Q is given 0.05. So your velocity will be 1.59 meter per second. Okay, is that 1.59? Then okay, now you get the velocity, you get every information as other except the F. How do you calculate, how do you find out F? Tell me, what do you need? Don't look at the book. Tell me, what do you need to find out the F? Anybody? What's the steps? Remember the steps. You need to find the F. Then it's a piece of cake for you. Okay.
You talking about with the Moody diagram?
Yes. How we use Moody diagram. Okay. Do you still remember what's the first thing you need to find out?
You said pick the blue arc first, the
yeah.
roughness.
Yeah. Can we calculate the surface roughness for this problem before we decide the blue curve? Look at the table I gave you. Is the asphalted cast iron on the table? Look at the table I sent you to in GroupMe. What is the K?
0.12
0. What's the unit of that?
millimeters.
Okay. So 0. Can you convert into meter for calculation?
0.00012.
That's right. Right? Divided by diameter. Diameter is also in meter. Be careful. It's the relative roughness. So what is the value for relative roughness? Yeah, don't read the book. Let's do the calculation ourselves.
0.0006.
Be careful, the zero number of zeros. So 0.0030 after the decimal, right? Then 6.
Yeah.
Is that right? Okay.
Yes,
Okay.
I think
Okay.
that's what I said.
Okay, good. Okay. So let's look at, do we have a blue curve for that value?
So is that unitless?
Is this unitless? Let me ask you.
It has to be, yeah.
Yeah, meter divided by meter, right? That's a good question. Hey, Josh, you have a good question. It's unitless, right? It's dimensionless, basically, okay? So in the Moody diagram, I think everything is dimensionless. You look at this Moody diagram, the Reynolds number is dimensionless. That's why they put the surface roughness also dimensionless. The efficient coefficient is dimensionless, right? Everything dimensionless. Okay, go ahead. Did you see a blue line representing 0.0006 roughness? Or not? If not, then you need to interpolate.
Yes, there is one.
There's one. Good. Okay, now we need to find the Reynolds number. Okay. Can you find Reynolds number? Oh, I need to give you the viscosity of the liquid, right? Nobody memorized that. Okay, let me see. What is the viscosity of liquid? Oh, 10.3, right? Example. Okay, the viscosity of water is, oh, easy. I can memorize that. 10 to negative 4 meters square per second. Yeah, that's viscosity. So calculate the Reynolds number for me. Do you remember the Reynolds number? Velocity times diameter divided by viscosity. Okay, give me the Reynolds number.
Can you give me that mu value one more time?
10 to negative 4. Did you see it? Do you see on my screen? I wrote it on here.
I was looking at my paper.
Okay.
Oh, okay, yeah.
Okay, yeah. So calculate. Let's see how fast you can calculate. How you use your calculator. Okay, you have 24 minutes again for each problem. You have to manage your time. That's why we need to practice.
I got 318.
Everybody agree? It seems like small to me. I'm not reading the book. Everybody else, do you agree? 318 Reynolds number? I don't think so. That's in the order of magnitude different. It's not 318. Check your calculation.
3.8 times 10 to the 8.
3.8 times 10 to the
3.184 times 10 to the 8.
what? 3.184?
Times 10 to the 8 is what I got.
Okay. Do everybody agree? I'm
Oh,
not
wait,
reading the book.
did you say 10 to the negative 4?
10 to negative 6 here down there. That's for viscosity. I don't think so.
Yeah,
I don't think Reynolds number will be 10
using
to the 8.
using the equation with the kinematic viscosity, that is what I got. 3.148 times 10 to the 8. It's a big
Okay,
number.
let me ask you everybody else. Do you agree?
Seems extremely big.
That seems too big to me.
I thought you had said 10 to the negative 4. When I did 10 to the negative 6, I got 31,800.
31,800.
Yeah.
Okay, that's smaller than 10 to the 8. So which one is correct? I want you to vote. You are the jury. Okay, I have two answers now. I think 318 is definitely not right. We already excluded.
Did everybody else get 1.59 meters per second for the velocity?
Okay, that's what on the book. So let's check it. And maybe wrong in the textbook. I don't know. Is that 1.59? Please walk with
Oh,
me. Yeah.
in the equation you gave us earlier, I might have wrote it down wrong. For the kinematic, I have density in that one. It should be in the other one, right?
Yeah, because it's a kinematic, so there's no density on the top. So you're actually 1,000 times smaller. It should be. So it's 3.18 times 10 to the 5. So okay, we're close. 31,800 is 3.1 times 10 to the 4. So which one is correct?
To the 5.
Now I got 318,400.
So it's to the 5.
Yeah.
Okay, so this is not right. Okay, see? Reynolds number calculation, it could be wrong. Many of you in the test, I actually see many of you did wrong on Reynolds number calculation. That's why I want you to practice here. Okay. Okay, as the engineer, of course, you really need to put the number right. Okay, so based on this Reynolds number, based on that blue curve, we decide, can you find an F for me? I'm out of space here. What is F? Now you need to read the table to see. You know, the F axis is, the Y axis is log scale. Is that log scale? It's difficult to read. But it gives you the mark, I think, on there. Okay, find an F for me. Let's practice it. Anybody?
I got like 0.017 or so.
0.0, it's close, 17. I think maybe it's right. Oh, anybody got a 0.017?
It's kind of hard on this small, on my camera,
Yeah.
on my phone screen.
Yeah. It's close, I think. Did you also get it 0.017-ish?
Maybe a little bit bigger than that point.
Yeah, maybe a little bit bigger, right?
Like 1.8, a little over 1.8.
Yeah, it's definitely less than 0.02. Okay, so maybe 0.8 or about 1.8 or 1.9-ish, right? Is that what everybody got? See, reading those tables is not that easy because the Reynolds number is not a a number that it's like hundreds or thousands. It's kind of in between. So you have to interpolate a little bit, get the straight ruler or something like that. I think in the textbook it says 0.019, but that's close enough. 0.18 should be close enough. Okay, based on the 0.019, can you calculate the frictional head loss to me? Give me a value, final solution. Maybe that was 1 point, but still, let's do it.
Dr. Zhang, I got a little bit lost whenever you were doing the Reynolds number. What value did you say was correct?
318,000. So 3.18 times 10 to the 5.
Okay.
Yeah. Well, the correct answer is in the textbook, but we just, I think this, eventually the value is not important, it's there. But we need to remember the process, okay? In the exam, I'm pretty sure I can say this. It will have the problem. You need to use Bernoulli use the Moody diagrams, okay? So you really need to know the process. Remember the process, and okay.
I got 11.63 meter.
11.3 meter. Good. Is that what
6.3.
everybody? Oh,
6.3. That's
okay.
using the 0.018 for the F.
Okay, that's fine. I think it's maybe slightly different with what the book have, but I don't mind. That's good enough. Okay. Any question to this one?
Yeah, why do we not use the second term in the head loss equation, the k times v squared over 2g?
You don't have minor loss in this problem. This is only.
I thought you said both those terms were just for head loss.
Yeah, it is for head loss, but in some situation you don't have those terms. If
All
you
right,
don't
so
have,
what about this makes it not use that?
if you don't have a component, if you don't have a fitting in that situation, it's just you don't have a valve on there, right? So the second term for K is for those components on the piping system, attached to the piping system. Okay, so the first term is the frictional head loss. So the loss from the friction. You know friction, right? Fluids over the pipe, it also has friction, okay? You have friction in the dynamics, right? So two solid surface have friction. But in fluid, there's also friction. So the first term is only for calculating frictional head loss. That makes sense, Patrick? Okay. So here, that's
Like say for a problem like this on the final, I mean, we could hypothetically all get a different answer, but you would just follow what we did.
Yeah,
And as long as it's close.
The value, I have a requirement. You don't get too far away. Let's say 10% up and down. It's acceptable. Okay, 10% up and down comparing to my solution. Plus or minus 10%. How about that? That's the industry standard. Usually your error is within 10%, acceptable, basically, right? Okay, is that good for everybody? Okay, this is actually a piping problem with only frictional hair loss. Right? Let's look at the 10.7. So if you're interested in the entire system, 10.7 is a more comprehensive figure. Okay, I said this. You have a tank. You have a pipe down here. Okay. Oh, in this problem, there's no pump. Okay, that make it a little bit easier. Okay, you have two surfaces. He asks you the elevation here. What elevation is needed? It's a gravity-driven piping system. So what elevation is needed for this to happen? Here, the elevation C2 is 130 meter. Okay, 130 meter. Okay, the dimensions, 130 meter for this portion. See, we have different portions, huh? 7 meter for the vertical, and 60 meter for this portion pipe. Okay. The elbows, how many? You have two bends here. Let's see. The diameter, 15 centimeter. Smooth pipe. What does that mean, smooth pipe? Give me an example of smooth pipe.
Stainless steel.
Stainless steel probably is not. Look at the table I sent you. It's on there. It actually has the item smooth pipe. They give two example of smooth pipe.
Glass
and plastic.
Like a glass line.
Yeah, plastic, PVC. Okay, that's often used, right? So PVC pipe we treat it as smooth pipe. Okay, so it's a smooth pipe. Okay, you have two two bands there. Okay, it gives you the R and D. Okay, the radius versus for the two bands, the radius versus the diameter of the pipe is 2. Okay, I guess you need to look at the. Can you turn to that figure I sent you, the minor loss case, the table, not the figure, the table. Okay, turn on your phone. Look at the in the group chat. 90 degree. You have 2 90-degree smooth band here. Okay. Look at the definition of R over D. With R over D, you have different Ks, right? Okay. R is the radius of the turn. Okay. D is the diameter of the pipe. Do you fully understand? Look at it. I see many of you are writing. Okay. This is in the video. You don't have to write, basically. Look at the figure. Follow me. Walk with me. Did you see that table on your phone?
You said it's the radians.
Look at the drawing there on there. Okay. 90 degrees smooth band. Did you see that picture?
Yeah, where it says with veins, R over D.
Yeah, left that we say with van left to that there's a diagram, right? Did you see there R in the diagram? Okay, so that's the definition for R. Okay, D is just the diameter of the pipe. Okay, so based on this R and D, now this case R over D is 2, right? It's given R over D is 2. So what is the K value actually for that 2 bands?
0.1.
That's right, 0.19. Okay, so basically that's just to test you the how to read this table. Okay. Now, can you do the calculation for this problem? It asks you what is the elevation need to be. So it's a gravity driven. So you need to be high enough. The gravity, the potential energy, gonna overcome the losses in the pipe. Okay. If the elevation is too low, the potential energy is not enough to overcome the loss. Okay. Okay. So again, you can write down the equation for that between 1 and 2. Okay. For this type of problem, always the first step to write down the equation. P1 over gamma. I know a lot of zeros in there, but hey, why not just write down the equation, earn some point from Dr. Zhang? Okay, that's what I like. You identify the correct equation first. Do I have pump in here? It doesn't seem like. Do I have a turbine in there? I don't think so. Okay. So we definitely have the loss here. Okay. So what is zeros? Anything 0 in this equation?
They're open tanks, right?
Yeah, open tanks, both of them. They are also, notice in the loss we'll talk about in a minute, there will be not only the 2 bands, but also this is a practical case. You have an entrance, inlet, and you have an outlet to the tank. Also, there will be case. Okay, so zeros. I really need to identify the zeros correctly. Okay, on those equations, always in equation 1 or 2 terms are zeros. Okay, so you need to find the correct 0 terms. Okay, anything else? Zeros? Give me 1 more minute. I wanted to at least complete this. Rest of them are easy. Your velocity are zeros on the 2 surfaces. Okay, so the Z1 is your unknown. Z2 is 130. So only problem here is just to find out the HL. HL is frictional head loss. I think you know everything. Now you need a velocity here. Okay, is it given velocity, the flow rate? I think it gives, right? Okay, velocity actually Q is given in this problem, 0.028 cubic meter per second. So you should be able to calculate the velocity just like the previous problem. Okay, plus summation of K, okay, V squared over 2G. Okay, what's the velocity here we're talking about? That's the velocity in the pipe. It's not,
Otherwise, it'd just be 0.
yeah, it's not the tank surface velocity. No, it's not. It's the velocity in the pipe. As long as there's flow, there's the velocity in the pipe, right? That's the V. I didn't say V1 or V2. It's just a V in the pipe, okay? So after you calculate the V, you should be able to find these terms. So same thing, you use the Moody diagram to find the F. Okay, L, D, V are all given. Case, there are 4 different cases. Here, since the pipe have the same velocity in there, so actually you can sum all the case together to times the same velocity. You can factor velocity out for easy calculation. Okay. Is that good? Everybody, any questions here? So that also inlet and outlet, entrance and exit, also find the K from the table. Okay, look at the table. Okay, so you should be able to find the K. K basically it's just a property. As long as you know how to read the table, you get those. Any questions to this?
The flow rate 0.04.
0.028 cubic meter per second.
All right.
Okay. Is that right? Everybody can calculate the velocity, right? That's in the quiz, right? It's a quiz you just did. Basically, it just asks you to calculate the velocity based on flow rate, right? This should be, everybody should be, right? Should be able to, okay?
Yes, sir. It's just the way you wrote it, it looked like it's a G.
That's fine. I guess you can
I'll
refer
tell
to your textbook, please. Yep. 0.028. Yeah, it's a cubic meter per second. Okay. Any other questions? Good. Okay. I'll let you complete the calculation. Go ahead, do practice yourself to use this problem. This is the more comprehensive problem. You have all the components there, all the case. Okay. See if you can correctly calculate it. Okay. The value, I can give you the final answer.
We did say the K is 0.19, but is that the number we reference with the chart? Because there is no 0.19 that I see.
There is. For R over D equal to 2, there's a 0.19 for K. What are you looking at? You're not looking at the chart. You're looking at that table for K. Josh, did you get it? You're not looking at the Moody diagram, don't you?
Oh, well, we just found the K from the, is that a different K or something?
We kind of K from the table. That's for one band. There you have
okay.
2 bands in here, plus you have an entrance and you have a exit for the pipe. Okay, so you have 4 cases in this problem. Okay, Josh?
Yeah, okay.
Okay. Very practical, not only for your final test, it's also for your job, okay? Do practice it, know how to do this, okay? You really can do some job as a mechanical, chemical engineer in the industry here, okay? If you know how to do this. Carefully calculate it, don't make a mistake, okay? Focus to yourself and try to practice it, okay? See you next Tuesday. I give you more review and a more actual problem. And prepare some questions if you have, okay? We can answer it to the class, okay? Is that good? Okay, see you next Tuesday.